Hello everyone. This video covers the basics of CMM alignment. So the basic idea here is we have 6 degrees of freedom. In other words, we have 6 different ways that we can move a part. So here I have Mastercam open. It has some great tools for manipulating parts, and I will start off in the transform dynamic command, and I'll grab a hold of this part and I will pin this gnomon directly to the center of the part. Now, notice that this gnomon actually has 3 different colors to it. It's kind of hard to see based on where I pinned it, so let me move that off just a little bit. Aha, much better. So this gnomon actually has 3 different colors. It has X, which is red, it has Y, which is green, and it has Z, which is blue. So the idea here is I can manipulate the part in any one of these 6 different directions, 3 linear and 3 rotary. Simply by clicking on different points of this gnomon. So if I click right here on this red line, this is a linear X translation. I'm moving linearly along the X-axis. Doesn't matter where I move the mouse. All it allows me to do is to move in the X-axis. Right? I hit escape to get out of that, and I click on the Y-axis instead. Notice that that allows me to move forward and backward. Doesn't matter where I put the mouse, it only moves the Y-axis. And of course, same thing for the Z-axis. I click on that gnomon. I'm just moving straight along the Z-axis. So those are the 3 linear degrees of freedom. Degrees of freedom just means that you can move in some direction. Now, of course, we also have different rotations. So you can see that the rotation that is associated with X is also colored red. That's this rotation right here. So if I click on that icon, that allows me to rotate this gnomon about the X-axis only. If I click on the green gnomon, this allows me to rotate about the Y-axis. And then if I click on the blue gnomon, that allows me to rotate about the Z-axis. So those are the 6 degrees of freedom. So now that we're clear on that, let's plant this gnomon. Let's plant this gnomon back over at the center of the part, and let's start manipulating the part a little bit. So we would assume that when we put a part on the machine, that it would sit perfectly flush on the fixture, and if you looked directly down at the part as the probe looks at it, you would see something like what we see here, and if you were looking perfectly from the front view, you would see this. But in the real world, a lot of times you put the part down on the fixture plate, and the reality is it's tilted off a little bit about the X-axis, so I'll take the part and I will manipulate that along the X-axis by about, let's say, 5 degrees. And then I'll also take it and manipulate it about the Y-axis by, we'll do 20 degrees. And then I'll just hit OK. And we'll come back and look at the top view, and now we can see a very different picture of this part. So if we just start inspecting features like this, we'll run into a whole bunch of different problems where the machine doesn't really know where the part is. So far I have only rotated it off in 2 different directions. So that's 2 of the 6 degrees of freedom. Now, some other things that could be wrong here. I'll go plant the gnomon right back where it was initially. We rotated this off about the X-axis and about the Y-axis. Well, this part could also be rotated off about the Z-axis. So notice what's happening here. I'm moving the Z-axis only. And it looks like that flat on the front of the part is not square to the X-axis of the machine as we'd like it to be. So I'll move this one 30 degrees. All right, so now we're rotated off in 3 different dimensions. Now I'll take the X-axis, and I'm going to move this linearly in one direction. So if you're counting, we've done the 3 rotary axes plus 1 linear axis. So we're off in 4 of the 6 degrees of freedom. I'll grab the Y-axis and I'll move that off as well. So now we're off in 5 of the 6 degrees of freedom. And last, I'll grab this Z-axis and I'll move that off as well. So when all that's complete, I'll hit enter. And basically our part is way out here in space. Okay, so the question is, how do we create a CMM alignment that can bring this part back over to the origin where it wants to be? And the answer is we have to do an alignment. So the features that we'll pick for this alignment will be the top plane, and we'll use that for our base plane alignment. So let's see how that will correct for this part. Well, I'll come up here to I'll come down here to create a new gnomon. And the first thing I'm going to do is pin this gnomon to the top of the part. Now you notice how the z-axis of that gnomon corrects itself as soon as I pin it to any surface. Right here it's normal to the front surface. As I move it to the top, it is picking up the normal of that surface. Now when I say normal, I just mean the line that is perpendicular to the surface. The line that is perpendicular about the x-axis and about the y-axis. So simply by pinning this to this plane, I have now corrected for the base plane of this part. So if I want to move the part onto the origin to simulate how a base plane alignment, quote unquote, fixes the x-axis and y-axis rotation, I'll end this command. I'll say OK to save this plane. And now I'll come up here in the Transform tab, and I will say Translate to Plane. So I'm going to grab the part, and I will translate it. I'll move it from the plane that I just created, in this case it's named plane, to the top plane, and I'll say OK. So what did that fix? Well, now if I look at the top plane, you notice how we are looking perfectly normal to the part. Essentially, what that has done, if we look from the front view, we could see that that has flattened this part out so that the top surface of the part is not rotated. Go to the right view here. It is not rotated about the x-axis, right? I'm moving the mouse to show you that we could rotate about the x-axis here, but we are nice and level from this view. I'll go to the front view, and now we'll be able to see that we are not rotated about the y-axis. So that takes care of 2 of the 6 degrees of freedom. Now, one of the options that we have in the base plane alignment is create origin in element. And to me, that's not very intuitive. What that really means is we can set the z-axis to 0 based on our base plane. So to set our z-axis 0 to that top surface, I'll simulate that here. We will go into the Transform tab, and we will say Dynamic, and I'll grab this top plane here, and I'll move the z-axis only down to the origin. And that is the end of that command. So looking from the top view, you can see we are nice and square to the top plane. Looking from the front view, you can see that origin in element command has set the z-axis 0 to the top plane like we want. However, we still have 3 degrees of freedom that are not accounted for. And those 3 degrees are the x-axis 0, really wants to be set to the center of this hole. Our y-axis 0 wants to be set to the center of the hole. And then our c-axis rotation, that's rotation about the z-axis, well, that also isn't correct. So let's correct for those one by one. Again, I'll come over here to the Transform Dynamic tool. I'll select the part, and I will pin the gnomon to the origin. So the next thing that we would do in a CMM program, after we touch 4 points on the top surface and level that out using our base plane, next thing we would do is probably touch either the OD or the ID. Really doesn't make a difference here because they're both concentric circles. And then we would say, we would touch 4 points on the circle, and then we would say create origin, and we would create the origin in the x and the y-axis. So when we create the origin in the x-axis, that essentially takes our x-axis by itself and moves it over to 0. And that looks partially good, but not completely good because it's only part of the story. The y-axis 0 also has to come up to the origin. So what I've just done here is the same thing as saying create origin in x and y axis, and we say OK. So if you're keeping track, so far I have controlled for the base plane alignment. That controlled for our rotation about x. It controlled for our rotation about y. And then if you say origin in element, it'll set the z0 directly to the top surface that you touched. Right? So there are 3 degrees of freedom for your base plane alignment. The next thing we did is touch 4 points on the circle and then created the origin in the x and y axis that controlled for 2 more degrees of freedom, that is linear x and linear y. And lastly, it looks like the only thing that we have to correct is rotation about the z-axis. So to fix that, we'll say Transform Dynamic. Again, I'll pin the gnomon directly to the center of the part. Looks like the only way that we have to manipulate this part to get it to be aligned with the x-axis, all we have to do is rotate about the z-axis. So you notice I've clicked on the blue arc here, and now I'm rotating exclusively about the z-axis. Now the issue here is I don't remember exactly where 0 is supposed to be, so I'll do this kind of approximately. I'm guessing it was probably about 35 degrees. And we'll look from the top view and see if that looks good. Nope, maybe it was 30 degrees. Ah, looks much better. So in conclusion here, we can see a graphic of the 6 degrees of freedom. Here you see we have linear x, linear y, and linear z. So that's 3 of the 6 degrees of freedom. You can rotate about any one of those axes individually. So if you rotate about x, you have A. If you rotate about y, you have B. And if you rotate about z, you have C. So it goes x, y, z, A, B, C, respectively. Now I've put this in graphical form over here. We have those 6 degrees of freedom right here. For linear degrees of freedom, we have x, y, and z. And for rotary degrees of freedom, we have A, B, and C. All right, so in the sequence of what we did here, at first the part was skewed off in every dimension it could be skewed off. The first thing we did was flatten out this top surface so that way it was not rotated about x, and it was not rotated about y. In that same command, we talked about using origin in element to create the z0 at the top surface. So how that looks in graphical form is this. In that first command, we flatten out our A and B using our base plane alignment. So we take care of our rotary axis using the base plane alignment. Now, if you decide to do origin in element, that will also constrain your z-axis 0 to whatever feature you use to do that. Now, again, we have linear here and rotary here. I've provided labels for each of those just to make them a little easier to read. We have the type of alignment first, the element type that is used to constrain it in the CMM software, and then the name of whatever surface we touched to constrain them. So for that base plane alignment, we touch a plane. The name of the plane would be top plane or datum A. Same thing here. All right, so after we level out this top plane, the next thing we did was touch, in the CMM software, we would touch 4 points on this inner diameter or this outer diameter here. Looking at the print, I think the outer diameter would be the preferred diameter. I believe that's datum B. So let's say we touch 4 points on the outer diameter, and then we say create origin in the x-axis linear and in the y-axis linear. In graphical form, we see our create origin constrains our x-axis linear and our y-axis linear as well. The element type we use to constrain that is the circle, and the name of the circle is OD for outside diameter. All right, at that point, the only thing we had remaining was the C-axis rotation. Remember, looking from the top view, it looked like this flat was not aligned with the x-axis. We touched in the CMM software, we would touch a line on the front surface of the part, and then we would say align axis parallel with axis to that line, and the line would be on that flat. So that constrains all 6 of our degrees of freedom. All right, now you may have also heard of a 3-2-1 alignment as well. So this is really looking at the same information through a different lens. In metrology, you learned about 3-2-1 alignments in the primary, secondary, and tertiary. This is why that is true. So when we did our base plane alignment, that constrained A and B, that's rotation about X and Y, and we also had the option of constraining Z. So there are your 3 degrees of freedom that you're constraining with your primary alignment. For your secondary alignment, we created our origin in X and Y, so that stopped us from moving linear along X and Y. So there are your 2 for your 3-2-1 alignment. And then for tertiary, which just means our third alignment feature, we align the axis to C. That means that we can't rotate about Z. So once you've constrained all 6 degrees of freedom, the machine can find the part and take some accurate measurements. So thank you for watching. I will see you at the next video.